What's up, everybody? Welcome to another video in this tutorial series on using the KITTI Odometry dataset with Python. I'm still getting my notes together to do the, I guess, maybe final video on doing the feature matching and visual odometry from where we've gotten so far, which is that so far we've gone from the fundamentals all the way through building the dataset handling class and then reconstructing the 3D world with our photographs and our stereo pair of images. And so I do have a little bit of time tonight, so I thought instead I would just make a short little video here to validate the results that we got from the depth calculations that we did with the stereo matching. Because usually when you're doing something like this, you want to make sure that your results are correct. Because if you start building, layers and layers on top of this thing, and you've done your math wrong, well, then you're going to run into problems down the road, and it'll get harder and harder to figure out where you made your mistake. So right about here, we can validate our depth estimations from the stereo, because even though we won't be doing LIDAR odometry in this tutorial series, I may go on to doing that later, that we are given LIDAR data. And that LIDAR data is a point cloud of XYZ points in space that are in the coordinate frame of the LIDAR sensor. And so the thing about LIDAR is that they're like any sensor, they have noise, and so their measurements may not be perfect, but when it comes to the difference between your stereo depth estimation and a LIDAR scan depth reading, you can probably be pretty sure that the LIDAR is going to be the more accurate sensor on that one. So I thought it would be informative and useful to what we can do is we can project the section of the LIDAR point cloud that falls onto our image plane onto an image plane that's the same size as the images that our camera is taking by first translating and rotating the point cloud into the coordinate frame of the left camera, and then projecting all of the points within the visual frame onto a image plane in the same way that you would with camera image points. And then we can compare the pixel locations of these depths with the depths that we calculated from the stereo image, and then see if our results were right on. And then as a bonus, since we have been then projected our point clouds onto an image plane, we can then make a fun little video of watching the car move through space from the vantage point of the LIDAR. So I thought this would be a fun little video here. So let's go over to the notebook. So I'm just going to pick right up where we left off from the last video. We have everything that I went through here, where we have the dataset handler loaded. We made the function to calculate depth from the stereo pair. And then now we have the disparity maps. We have our depth map. And we did the mask. And so here we are. And so we know that our handler object that we made has a first point cloud loaded into it. And I've pulled up the shape here, and then we can see we have 124,000 rows, which are 124,500 points. And each one of these points has an XYZ location, and then the fourth value is reflectance. And so we can project this onto the coordinate system or the image plane. And so one of the things that we have from our calibration file was that TR matrix. If we take a look at that, if we round it, it'll be easier to look at. Okay, so here we go. This is a transformation matrix. It's got a rotation matrix is the 3x3 portion here, and then this is the translation vector. And what this transformation matrix is doing is taking points in the LIDAR point cloud and moving them into the coordinate system of the left camera. And so there's going to be a little translation involved in that. And actually, let me pull this up real quick. It'll take just a second to pull that the car schematic back up so that we can get a visual look at at how the sensors are set up. As a matter of fact, I can just pull it up over here. So we'll just do KITTI dataset and go over here, go to setup, and they've got the image here. Okay, so this is the Velodyne, this is the LIDAR scanner. It sits pretty much directly behind the camera, but you can see that the axes point in different directions. So the camera, as per standard, has the z-axis facing forward, x-axis goes up to the right, and then the y-axis is positive downward because it's a right-hand rule coordinate frame. And this Velodyne scanner has a x-axis pointing forward and the z-axis pointing up. It's still a right-hand rule coordinate frame, but it's just oriented differently. And this will be accounted for in this transformation matrix. So as long as we apply this transformation matrix to any point in the LIDAR point cloud, it will put that point into the coordinate frame of our left camera, and it will make sense in that way. So this is what we need, and we have it, you know, attached to our dataset handling class. So let's put it to good use. So we're going to make a function here, and it's going to be called point cloud to image. And this is also in the notebook, in the repository, like all the functions are, with a bit more documentation. And this is a useful function because, well, for the reasons I mentioned, we're going to be able to validate our depth estimations, see how much they agree with the point cloud reading, and then we can also make a cool little video out of it. So we'll take in a point cloud, we'll take in im height, we'll take in im width, and we'll take in that transformation matrix, and then also the projection matrix for the left camera. That'll give us the intrinsic information that we need to turn the information into pixel locations so that we can match things up to the images. So you might be wondering at this point, well, if the LIDAR is so accurate in its depth estimation, then why didn't we just use that to get our depths from, rather than doing the stereo pair of cameras? And the answer is because the point cloud is sparse. So you'll see this in a moment, that there's not as many dots that fit into the image plane from the LIDAR as you might think. There's a lot of empty space there. So we wouldn't really necessarily have information in the places that we need it, because we're going to be finding features in the images and then matching them to other pictures. So we need the locations of those features to have depth information associated with them, and the stereo depth is giving us much more continuous information, with some missing values granted, but the LIDAR is much more sparse. So we'll see that in just a second. So we've got a function going here. It's going to take a point cloud, and so I'm going to split the reflectance information off and just say that that's the point cloud, all rows, third column, which is really the fourth column. And then, because maybe we can color it with that might be cool, but it's not going to help us with our 3D Euclidean space. So then, as a matter of fact, first, this is an important thing to think about when you're working with these really big matrices like these point clouds, is that when you're doing matrix math, the size of your matrix is going to obviously increase the amount of computational power that you're going to use to do any mathematical operation on that matrix. So if we know that our image plane is in front of this camera, and the x-axis of the Velodyne scanner points forward, then anything with a negative x-coordinate in the coordinate frame of the Velodyne scanner isn't going to appear on our image plane of the camera. So we can just ignore all of that. It's not going to be useful at all to us. And so let's just go ahead and trim our matrix to be exactly that way so that we can speed up our operations here. So we're going to say all rows, okay, so point cloud equals point cloud, where the point cloud, all rows, first column is greater than 0. And so that's going to help. And just to make that clear, let's copy and paste this cell, and I guess it would be easier if this was assigned to a variable. We'll just call it pcloud equals that, and then we'll say print full pcloud shape, and do pcloud.shape, and then we'll do pcloud, okay, trimmed pcloud equals pcloud where pcloud all rows, or yeah, first column. And remember before I said you could have transposed this matrix to begin with, and that it really didn't matter. But I'm just going with the convention that I used in the second video, where I set it up as rows are the points and then columns are the XYZ reflectance. Could have been the other way, and indeed we will be transposing it. So, but just, you know, keep track of how you have this set up. Okay, so and this is greater than 0, and then let's see, print trimmed pcloud shape is trimmed pcloud. Yeah, there we go. That shape. Yeah, so obviously, I mean, I guess we could have kind of worked that out in our heads, but it's half, because you've cut half of an axis completely out of the picture, so that'll speed things up. And so we've got trimmed down to the information we want. We'll get rid of the reflectance, well, not really get rid of it, but we'll just isolate it into this one variable here. And then, so when, like I talked about a lot in the first video, when you're applying a transformation matrix to 3D Euclidean space, you need to move into homogeneous space. And you can do that easily just by adding a 1 to every XYZ coordinate. So it'll be XYZ1. So you go from 3 dimensions to a 4-dimensional homogeneous space, which is really the same thing. And so that 1 is going to allow you, as you multiply through, you'll say X times this, plus Y times this, plus Z times this, plus 1 times this, and that'll allow the translation vector, which is these 3 numbers here, to just be added on to the position after the rotation is being applied to that particular element of the vector. And so that's why that's done. So we need to make our point cloud homogeneous. So we're going to say now that point cloud equals point cloud, or rather it's going to be, we're going to horizontally stack, which in NumPy it means, like, if you have 3 columns, then we want a column, excuse me, of 1s over here on the right. So I'm going to take the 3 XYZ columns off of our point cloud, and then I'm going to horizontally stack a row of 1s onto the right side of it. So we say np.h stack, and then it takes a list of things you want to stack together. So we'll say point cloud, all rows up to the 4th column, and then we'll do np.ones, which will be a vector of 1s in whatever shape, or a matrix of 1s. Point cloud dot shape 0, which will be the number of rows that it has. So this will be a vector of 1s the size that we need, except that it will be a horizontal vector and we want it to be a vertical vector. So we're going to say reshape -1, 1. And that's sort of a weird thing about NumPy, because you would think that you could just say transpose, but you know, play around with it yourself. But you'll see that if you take a NumPy array and then just transpose it, it's exactly the same as it was before. And if you really want to get it to be a column vector, you need to use this reshape -1, 1. And so that'll be the list of things that we're horizontally stacking. And okay, so now we have a homogeneous point cloud. So let me put a little comments in here just in case, you know, people are following along. Okay, make point cloud homogeneous. and we'll just say x, y, z, 1. And so we've taken the first three columns, x, y, z, and then we've stacked on np.1s reshaped into a column vector. And okay. So now we can go ahead and put this into the 3D coordinate frame of the camera. So we're not projecting it onto the image plane yet. We're just moving all these 3D points from the coordinate frame of the LIDAR into the 3D coordinate frame of the camera. And we can do that. So transform points into 3D coordinate frame of camera. And then we'll say cam xyz equals tr dot point cloud, and then we'll say dot t. And that's because when you're doing matrix math, you need to have the number of columns in your first matrix match the number of rows in your second matrix. So this is why a lot of times people do just lay out x, y, z, 1 or the rows, and then the columns go on forever for every point that you have. And the reason I set them up as x, y, z as columns with the rows going downward is because in my head, you know, that's just how I think of it. But really, when you end up doing the math here, you want x, y, and z to be the rows, and then your columns go on for every single point. So all we have to do though is just add this little dot t to the end, and it'll take it from this to that, just like that. 2 characters, dot t. So there's really no reason to worry about how you're doing it. You just got to keep track of which way you're doing it. And then so again, I think we're gonna just clip off anything that has a negative z coordinate from this, because again, you know, we just want to save as much computation time as we can. So we'll just say cam xyz equals cam xyz where cam xyz. And now in this case, it's going to be trying to think. Now I'm confused. Let me think real quick just to see what shape you get after you mold. I'm pretty sure it's going to be rows by columns. So it should be, if we do handler.tr.dot of the trimmed pcloud.t, and we'll just take dot shape of that. Yeah, okay, so you see we got 3 rows and the number of columns that correspond to the number of points that we have. And notice how that when we take homogeneous coordinates, apply a transformation matrix, then what comes out on the other side is no longer homogeneous coordinates. Now they're just 3D Euclidean coordinates. So if you were going to apply another transformation matrix to those coordinates, then you'd have to add the 1s again. So it's just something interesting to keep in mind. So I think, so this will just be where cam xyz second row is greater than 0. And that'll keep, you know, just clip off a few more points to make the math even easier. Probably didn't have to do that though, but you know, let's be thorough here. Okay, so now we know that the depth that we're looking for is going to be the z values. So because now we're in the camera's coordinate frame, so this is just going to be cam xyz second row, and that's the depth that we're looking for. And okay, so now we're ready. Now that we have right, so the way that we're going to do this is because we have the depth of all of our point cloud 3D points. Then we're going to project those points onto a 2D image, and then for the pixel locations that we project them to, the value of that pixel I'm going to set as the depth that it used to have, so that the brightness will correspond to how far away it is. And we may end up reversing that so that brighter things are closer to us, but for now, let's just keep it simple and say that we want to get our pixel coordinates, or rather, we got to project the thing first. So we'll say projection equals PO, which is our camera projection matrix, dot cam XYZ. And in this case, we do need to go ahead and make cam XYZ into a homogeneous coordinate system. So let's go ahead and do that. We'll say np.hstack, same thing we did before, a list of cam XYZ, and then np.ones in the shape of cam XYZ.shape 1, in this case because it's going sideways, and that should be enough. Okay, so now then we project those points onto a plane by using the projection matrix of the camera. And so the thing about when you've done this, so let's kind of follow along in this cell up here so that we can kind of see when you're building inside of a function, sometimes it's helpful to like work outside of that function to really see what you're doing. So let's say this, the same thing out here, cam XYZ equals this thing, because now you know what I didn't do. We'll say homogeneous pcloud equals trimmed. That's going to be np.hstack of the trimmed pcloud, all rows up to the 4th column, np.ones in the trimmed pcloud.shape 0, and this time we're going to have to do the reshape, -1, yeah, because that'll make it homogeneous. Then we do cam XYZ, and then we can say projection equals handler.po. We got to make that homogeneous, so let's just go ahead and do that as well. This happens all the time when you're working with projections. And then np.ones in the shape of cam xyz.shape, number of columns, and we don't have to reshape it because we're already in a horizontally running matrix. And then so handler.po dot cam xyz, and let's take a look at some values from our projection matrix here. So that's going to be a horizontal matrix, so we want to do all rows, and we'll say the first 5 columns. And take a look. Int object has no reshape. That's because I closed that in the wrong place. So go back. Got another problem here. All the input arrays, same number of dimensions, and that's coming from okay, let me just run through this real quick, figure out what I've done wrong. Shape 0, it should be the number of rows, so it should be the right size, but it's yelling at me for some reason. I can't figure out why. So we've got yeah, because it's trim pcloud shape. This is the number of rows. We took it up to the 4th column. We're trying to stack trim pcloud all the rows, which pretty sure is I mean, we're literally using the shape of trim pcloud here. yet it is yelling at me. Just gotta think. So let's just run through what is trend pcloud.shape. Yeah, I mean, duh. So let's think. Why does it not want me to put np.1's pcloud.shape 0? A little bit of a problem here. What does it really say here? The array at index 0 has 1 dimension, the array at index 1 has 2 dimensions. Sorry everybody, I'm running into a little bit of a snag here. Just doesn't make any sense. If I write exactly that, trim pcloud 3, and then if I say .shape, okay, so we got, that's what it is. I have to have a colon here because we want to take it up to the 4th row. I was just indexing the 4th row, which is not the same thing. So, man, really hitting it here. All the input arrays, and it's, so I've probably done something similar. Okay, you know why? Because this is an H stack, and we're actually trying to do a V stack. So now we know. So, and then I want to do a .t here because it's easier to look at, so that kind of explains why I prefer to have these be vertical. Okay, so now that we're finally here with some numbers in front of us, the thing to notice is that we have indeed used a camera projection matrix to put these into pixel values, except that these pixel values have decimal places. So they don't have clean XY pixel locations. They're going to need to be rounded to figure out where these 3D points should go on an image, because we can't really assign them in a NumPy array that is the shape of our image. We can't say, all right, this point goes at pixel or X location 8076.92. We're going to have to go ahead and round these to the nearest number, nearest integer. So we can go ahead and fix this V stack problem here because I already see that one coming. And then we need to round these things. So we'll do pixel coordinates equals np.round, and it's going to be projection.t to 0 decimal places because we want them to be integers. And we're going to take all those rows up to the 3rd column, which I don't really think is necessary. Let me leave this out for now because I don't wrote that. And then we're going to do as type int because if we're going to be indexing using these values, then they need to be the data type integer. So let's go ahead and see what that looks like up here. Since we're working outside of the function, we'll say pixel chords equal projection. Sorry, it's supposed to be np.round. You just erase the whole word, even though, and then 0.t, and then we'll look at pixel chords, this many of them. Okay, perfect. This is exactly what we want, except they're not ints, so we need to do as type int. Beautiful. Now they're integers. We can index with those. And so you notice that there are still z values in these pixel coordinates. So that's exactly why we do need the indexing that I just about erased here, where we're going to say all rows, but we only want up to the 2nd column. But that is not... Let me think real quick. Kind of getting ahead of myself, just winging this thing, but feel like these definitely need to be divided by their z values. Yeah, I missed that. So we need to say that let's do it here. So cam xyz equals cam xyz divided by cam xyz, the second column, or rather in this case it's the second row because it's a horizontal matrix at this point. And so if we do that up here, let me just make sure I'm doing this right. Sorry, I guess this is kind of more complicated than I thought when I started the video, but you know, it's all going to work out. So hopefully you're following and you get what I'm doing here. That, like I said, if we're going to project onto a flat image, then we need to divide out the depth, because when you divide everything by its own depth, then all the depths become 1, and then you're on a flat plane, a depth of 1 away from yourself. And so before we stack the homogeneous ones on the end here, we should already have done that here. I guess we could just say divide equals cam xyz, save a little time, and then I'm going to do it anyways. Second row. And so now, if we look, cool, we can see that this last row is all 1s. Right, and so we should have noticed before, because if I take this away and do this again, like, we don't have an image size being, well, actually I can't make that point, but anyways, it's important to divide by the depth, y'all. So let's go ahead and do that. Make sure that we're doing things right. I'm going to clean up this notation here and say divide equals z values. Then we'll put it into homogeneous coordinates. And you know what's funny about that is that you don't even have to do that if you're going to do that, because this will make the z values 1. So we'll actually have a column of 1s there, so there's really no reason to stack them on. Oh yeah, there is. You can do these things in different orders, and that's kind of like what's beautiful and also sometimes a little confusing about this, is that you can divide by the depth while you're in meters, or you can divide by the depth while you're in pixels. It really doesn't matter, because what you're actually doing when you divide by the depth is you're moving into normalized coordinates that don't have units. And then once you do this PO dot dot, that's when you're reapplying the pixel units to your normalized coordinates, and that's when you're back into units again. So it's kind of interesting that this division by the depth can really happen at any point in the process. I mean, once you're in the coordinate frame that you want to be in. Okay, so we've got our pixel coordinates, and they're integers, and we're doing fine here. Now, excuse me. So now we need to only think about what's in our image plane. So we're in proper pixel coordinates now. We've applied the projection matrix, which includes the intrinsic matrix, which includes the origin offset that brings the origin from the center of the image to the top left corner of the image. Now we know that any pixel values that are less than 0 in either the U or the V direction will be outside of the image, because an image doesn't have any negative pixel coordinates, and that any pixels that are greater than the width or the height of the image in those corresponding directions will also be outside of our image. So we don't need anything that is outside of our image. We're only trying to make an image out of this point cloud. So we're going to make a variable indices. We're going to use np.where, and then we're going to use a bunch of, you'll see. So we're going to say where pixel, just make sure you're wrapping these in parentheses. Coordinates, all rows, first, yeah, because I transposed it here. So we're back in a vertical matrix. So all rows, first column, so we're talking about U, which is the horizontal pixel coordinates. And so we want that where we're less than the im width, because anything the im width or greater is going to be outside of our image plane, because we start at 0. So the im width is counting the number of pixels you have, including 0. So we don't want to say less than or equal to, because that would be an extra pixel, and we don't want that. So we say less than im width, and then we say and we want where pixel coordinates. So these are all going to turn into Boolean arrays, and then you're adding these ands to combine these Boolean arrays, and this will give us something that we can index our pixel coordinates with here in a moment. So we'll also say that we need these to be greater than or equal to 0, because that's our starting U value. And then so we'll come around again, we'll say and where pixel coordinates, in this case all rows, and the V values we want to be less than the M height. Oop, no comma. And then and where the pixel coordinates, all rows, Y values are greater than or equal to 0. And this will successfully limit our scope of interest to the image plane that our camera has. That we will send in the im height and the im width information into the function later. And we, of course, we know it's attached to our handler class, so that'll be super easy. And so now pixel coordinates are just going to be equal to pixel coordinates where we are indexing, because that's all we care about anymore. And same with the depth, equals depth in the places where we are interested. So we're working with smaller arrays now. We've limited our scope of attention. And then so I'm going to make this object render, which for now I'm just going to say is np.zeros in the shape of im height first, because that's how, you know, NumPy does the height first. It does rows and then columns, so then we'll do im width second. And then we're just going to iterate over our pixel coordinates that we've been given. So this is why I set it up as np.zeros, because now we have a matrix that has a 0 value for every single pixel location on our image plane. And then now we can use these these rounded locations of the projections of 3D point cloud points onto the image plane. We rounded them to integers so that we can index this rigid grid of pixels and then place them on there where they go. And then the value I'm going to give them is going to be the depth that we were given at that time. You know, I'm actually going to, I didn't do this earlier, but just it could be fun. So we'll say reflectance equals reflectance indices. Because maybe we can do some color with that or something. I haven't tried that yet, but we'll try. We'll see what happens. So what I'm going to do is I'm going to use this variable j to count, because our depth here is not two-dimensional. It's just a long list of points. So this j, as we enumerate our pixel coordinates, so this is going to give us a number that keeps counting as we go through each of our UV two-dimensional pixel location tuples, and that'll be very useful because we can use J to index into our depth. So we'll say if U is greater than or equal to M width or U is less than 0, which it shouldn't be because we filtered that out up there where we did this np.where statement. But I guess this is just a probably left over from before I did that, but it never hurts to be super duper, you know, I don't know. This probably doesn't need to be here, but I'm just going to type it anyways because it works. And really, this is doing the exact same thing that this does. And if I had more time to play around, I would compare to see which is faster. Is it faster if you index it this way, or is it faster if you loop through this way? And I would be willing to bet that it's faster to do it with the np.where, because otherwise you're going to be iterating over a lot of pixel coordinates that you're not going to be using. So that's why this is up here now. And I probably should have gotten rid of this, but we'll just run with it. But just so you know, that's what's happening. So in this case, the pixel coordinates have become UV because they were X and Y, and so they're saved as UV tuples, but because we're indexing into a NumPy array, we want to reverse it and go VU. Probably obvious to a lot of people, but you know, whatever. And then we're going to set the value of this pixel location to the depth indexed by our constantly increasing J value that will correspond to the point that goes there. And so I think that's it. You might get an error, but that's the end of this function. So we have taken in a point cloud. We've limited our interest to only things that were in front of the LIDAR, because those will also be things that were in front of the camera, and we don't need any of the other information to slow us down. And then we transformed those 3D coordinates. First, we made them homogeneous. Then we transformed them using our TR, which is the transformation matrix between the LIDAR and the camera, which takes us into camera XYZ coordinates. Then we were a little redundant and took the camera XYZ coordinates only where Z is greater than 0, because again, in front of the camera. Then we took the depth, shaved it off here to save it by itself, so that we could then take cam XYZ, divide it by its depth to give us a flat projection of the 3D world. We turned that into homogeneous coordinates. Then we projected that onto an image plane in pixel units by using our projection matrix for the camera. We rounded the pixel locations of that projection to integers so that we could actually assign them into pixel locations on our image plane, so that we can you know, do that down here. We found the indices of pixel coordinates that actually fit on our image, aka they do not have negative U or V values. They start at 0 and they go up to the width and height of the image. We then reduced the pixel coordinates, depth, and reflectance information using the indices that we got from the np.where. And then we iterated through our remaining pixel coordinates and assigned the dot at those coordinates the depth that we got from the LIDAR scan. And so now we should be able to say render equals point cloud to image, and then we'll pass in handler dot first point cloud, and it also needs m height, m width, tr, and po. So we'll just break the line here. We'll say handler dot, let me just pull this up like that. m height, handler.mWidth, handler.tr, and handler.p0. It looks right. M height, m width, tr, p0. Right on. So that should give us a render. No errors. What do we got? So index did not match index array along dimension 0. Okay, so what we got? T, negative z values. Okay, I see why. Okay, so we still need all of our rows here, and then we want the columns where the second row of that column is greater than 0. So I got a little confused there because this is a horizontal matrix. So we still want to keep all of the rows the whole way through, but we're going to drop the columns where the third row, which is the z value, is 0 or less. So that's what's happening there. And we still have another error, zeros with an E, which is something I do a lot. All right, now we got it. So let's say fig equals plt dot, or rather I don't have to do that, plt dot figure, fig size equals, do 11 by 7 here. Let me add a little space so y'all aren't going blind staring at the bottom of the screen. And we'll say plt.show the render. And we have a problem. Truth value of an array with more than one element is ambiguous. And that is happening. First of all, let's just see render.shape. It's going to have values. I don't know why that's not happy with me. I think for a moment. We have a render. We're trying to tell PLT to show it. Oh, it's mshow. I'm sorry. There we go. Okay, so here we see it. We can see, you know, I don't know how clearly you can see this in the video. Let me bump the size up here slightly. Call it 13.5 maybe. That'll look a little better. But you can see it here. I mean, it's obviously exactly what I was talking about. You're projecting dots from a point cloud onto an image plane, so there's a lot of empty space. We can see that the LIDAR does not hit above a certain height because this is pretty classic. You know, there could be a lot of data up here, but there's nothing that the car would be tall enough to hit, so really nothing that the autonomous vehicle would be that interested in at that height with this scan. So they've cut this LIDAR scan just doesn't go any higher than, like, you know, maybe looks like 2 car heights up or so. And right now we're using the depth as the intensity essentially. So things that are further away are actually going to be brighter. And that's kind of even hard to see because it, you know, it all kind of looks a lot the same. But, you know, one thing that we can do, we can just say, do it over here. At this point, we're just talking, oh, so before we do anything tricky, we can see we have our functions worked. We have made a image render of our point cloud onto a 2D image plane that's the same size and in the same coordinate frame as the camera. So let's do a little A/B comparison here because we have a depth estimation from earlier using our stereo to depth function that we made in the last video. And so it's called depth here. And so if I say y I'll say d enumerates depth. And let's say print, and we'll say stereo depth colon, and we will do D, which is the stereo depth, and then we'll say LIDAR depth colon, and we will do render dot. Okay, so I think we're gonna have to flatten these because these are 2D things. So yeah, we'll say render dot flatten. And then I think after, like, you know, maybe 500 of these, we'll have enough so that we don't have a, you know, list of a million things. So we'll say if I is greater than 500, then we'll break. Okay, so I screwed up and I didn't put the index on here, so I have to put the I there. Okay, so this is really going to show that the LIDAR depth is 0 wherever it doesn't have information, which is basically almost half the image going downwards. We don't want to look at any of that. So what we're going to do is we're just going to filter out for anywhere the LIDAR doesn't, because remember I started with an np.0's matrix, so that's why any place where the depth is 0 is missing information. Plus you wouldn't have a depth of 0, or otherwise something would be hitting the LIDAR. So we'll say if render.flatten index is equal to 0, continue the loop. It's going to take a while to get through all that missing information at the top here. Oh. You know what the problem is that we have to interrupt this because I is counting up. How can I just gonna make this easier on ourselves. That would be super duper. We're just gonna say depth from the, so what's our im height again? Handler.im height. I thought this was going to be a fun little short video, but apparently it's a little more involved than I thought, but it's totally all right. So let's say starting at 200 on for the rows. Yeah, because that'll be the vertical direction, and then all columns. And we'll say the exact same for this as well. 200 on all columns, and we have to do that over here as well. 200 on all columns, and let me just comment this out for a second. Okay, so now we're getting only ones. Oh, shoot. Okay, so I can already see what's happening here. Is that I've divided by the depth before. Excuse me. No, I didn't, though. So what happened? The depth should... Oh, you know what? I'm using a name of a global variable here, which is gonna get us screwed up. So let's repeat this process, but I'm gonna call it stereo depth instead of depth. So stereo depth. Okay, we're still getting a bunch of ones on that. Oh, you know what it is that this is something that's so confusing with Python sometimes, is that I've assigned cam XYZ the 0 to be depth, and it still points, depth still points to this actual thing. So when I do this operation here and say cam XYZ divide equals cam XYZ2, not only does it change cam XYZ here, it changes it here, and so depth actually changes along with it. So if you want to not have that happen, you have to say copy. So that is some good Python knowledge to have, because that can really screw you up and it can be hard to debug. So now we're cooking. Looks like it took a little longer this time. Or, oh, it's because that's still going on down there. I should have had some water over here or something. Okay, yeah, this actually looks way better. You remember I made the remark earlier that I said all these brightnesses kind of look the same, and they did, because they were all 1. So that really explains a lot. Now we can see much more that this looks like depth is being reflected here, where it's bright over here, it's further away, and then up close to us we can barely see anything. And so that's fine, because we'll adjust that and make things better looking in a second for our own benefit. But all right, so here we go. We got some real stuff going on. As a matter of fact, this is still going to take forever, so let's uncomment this exit criteria over here. So probably a little higher than 500 is necessary. Let's go for 1,000. Okay. So cool, we're there. You can see that these numbers are pretty close all the way down. I mean, there's some discrepancies here, and that's because stereo depth estimation is not perfect, and the LIDAR isn't perfect either. So I would just say that between the two of these numbers, I would trust the LIDAR readings more. But the good news is that they're mostly the same, which means that all of our math is worked out, and that our stereo depth map is indeed giving us realistic depths, because we have projected our LIDAR points onto the image plane, and we've literally laid them side by side next to each other. And we can see that these depths are lining up within the meter in a lot of cases here. And you can see these max values here where the stereo disparity didn't know what was going on, and these are the ones that we're going to filter out later. But yeah, I mean, okay, so here's some interesting ones. We got 7.8 versus 15. Those are not exactly the same thing, so, you know, a little bit of disagreement over here. But when it comes to the vast majority of these values, they're right in the ballpark, you know, within a meter or two. So this looks really good. And then so, okay, we have validated our depth estimation results, which was sort of the point of this video. But so, you know, you can exit here, or we can do something fun and make ourselves a little video with these LIDAR renders. And so to go ahead and do that, let me say, for every time we're going to start this process, we need to say handler.reset frames, because we're using the low memory handler that loads the point clouds as you need them. And so every time you terminate that process, it's going to stay, the pointer on the generator is going to stay wherever it was when it stopped, which may not be that bad of a thing, but we'll just have this up here. And okay. So this is going to be interesting. We're going to say point cloud frames. And what I'm going to do is I'm going to make a generator that runs the items taken from the point cloud generator attached to the class object and run them through the function that we just made to turn them into renders. So this is going to be a generator that generates renderized versions of the generated point clouds from the class generator. So, and we'll see how that works. So it's when you do a list iteration for a generator, well, it's not a list iteration anymore, but it's an iteration. You'd use the parentheses instead of the brackets. And we say point cloud to image. And then, so now we're making a generator of a function call. And the first thing that goes into the function is our point cloud, which is going to be the next handler.pointClouds, which is going to pop off a point cloud every time it's called. And so that's what we want. And then we need to go ahead and pass in the imHeight, the imWidth, the handler.tr, and handler.po. And this will be a successful function call. And then we need to tell it for I in range handler.num frames, which is our useful little data to let us know how many there are. And then so, let me think. Let's just stick with the point clouds real quick. I may get crazy with it here in a second. This is all for fun, by the way, so, you know, hopefully I'm probably going to call this video like 4.5 because it didn't necessarily get us a lot further toward the visual odometry that I've been promising you this whole time. But I think that it was a good thing to cover because it showed, it's just, I don't know, it's just showing all the stuff we've been working with in a sort of a different fashion. And also we validated our, you know, we checked our work on the depth estimations because we're going to be building our visual odometry off of those depth estimations. And so we wanted to make sure that they're right. And so we see that we've done a good job. Great. Now we get a little bonus with the video. So yeah, and I think let's have some fun here. We'll do GT for GT in handler.gt. So these are going to be our ground truth poses, and I'm going to chart them over time as we go through space. And then you know, let me leave this out for now so I don't run too many things at you at once. You know, let's just look at our point clouds real quick, and then yeah, we'll get there. So let's do for I in range of, let me use the num frames, and we'll say 4 to 50, and then we'll just say cv2.imshow. Okay, so I don't know if I've showed you cv2.imshow yet in this tutorial series. It's pretty cool. It will open up a new window to show you the image outside of the notebook. So I'm going to have to switch to full screen here. And that you just have to use it properly. And so when you do, the first thing you pass is a string that's going to be the name of the window that it's going to create. And so in this case, we're going to call it LIDAR. And then we're going to say next pcloud frames, because that's going to pop off another generated item. I don't know if pop is the right word there, but it's going to generate a pcloud frame every time this for loop comes around. And we're going to imshow that, and then we're going to say cv2.wait key and wait for a single millisecond for now. And then at the end, so this is what I'm talking about with cv2.imshow, is that you always got to do like 3 things. You want to call the imshow, make sure you give the window a name. You need a wait key. If you put 0, it's going to wait until you press a key. Otherwise, it's going to wait the number of milliseconds that you write into this argument. And then you want to say destroy all windows. and then that'll clear the window so you don't have like a not responding window showing on your desktop. It's very annoying. So let me switch to full screen here and clean up things for you visual pleasure. And I'm actually going to make sure that we're looking at full screen, and we are. So let's run this. And we get an error. Dataset, and there's no imwidth. Imwidth. There we go. And expected 2 arguments, and it got 5. Okay, that's because I needed to close this to make that next call, and that's where that parenthesis was supposed to go, because the first argument into this function is the next handler.pointClouds, and then all of these actually, if we were being good with our formatting, should sit back like this. All right, here we go. So pretty cool. We're cooking through time here. I don't know if there's a way to use that reflectance information for color there. That would be kind of cool, but I don't know how offhand, so I don't want to like make this video another half hour while I sit here and figure that out, although it would be cool. So, you know. Yeah, it would be cool. I'll have to figure that out. Maybe I'll do that some other time. But anyway, so clearly that has worked. So I didn't reset the frame, so you can see that we're picking up where we left off there. And this is probably going to be moving a little faster than the car was actually driving. But, you know, it's pretty cool. So we can see the point cloud there. And, yeah, how long is this video now? Because, I mean, I could go on with this making stuff. Yeah, we're at an hour already. Yeah, I don't know. I don't see why not. Let's just keep rolling with it for a little while here. At any point you can stop watching. I'm just gonna be having fun with making little videos at this point. So, you know, I think it's all fun. You know, when I was learning Python and stuff, videos like this would be pretty cool to watch, because seeing somebody use all these functions and different indexing methods and just like, you know, built-in Python functions even, you know, that just I didn't use often would sometimes be really cool. So I hope there's somebody out there that's thinking the same thing. And so let me open up my cheat sheet over here so I can do this. So I'm going to make this as brief as I can. So what we're going to do is I'm just going to kind of copy this and explain it as I'm doing it. So I'm going to make an empty list of x's, empty list of y's, and an empty list of z's, because we're going to be filling these up with the ground truth poses as the videos occur, so that I can plot the path of the car as we watch the videos, which I think will be cool. And then we're going to do compute times is an empty list, fig equals plt.figure, and then we'll say ax equals fig dot add subplot projection equals 3D. Okay, and then what is the call for that? I think it's matplotlib tk, if I'm not mistaken. Had to figure it out. It's around here somewhere. I'm pretty sure it is. I don't know what else. I'm surprised I don't have it over here, as a matter of fact. But yeah, I think so. There's matplotlib notebook, which gives you the 3D slider where you can move things around. And there's matplotlib inline, which puts your graphs into the notebook in line with your cells. And then there's matplotlib tk. I'm pretty sure it's tk. We'll figure out in a second. Lib tk. Now, there's something, you know, matplotlib is a touchy, fickle thing, and it does not like If you tell it to be in notebook mode before you tell it that you want to see something in, or I'm sorry, if you tell it that you want to be inline before you want to be in notebook, the notebook mode won't work. But if you do notebook and then do an inline, then you'll be able to switch back and forth. But if you do notebook at any point, you won't be able to do TK at all. And if you do TK before you do notebook, you won't be able to do notebook at all. So as you're running your Jupyter Notebook, you kind of want to keep track of what your intentions will be in the future, because you get far into something and then you realize that you can't use matplotlib TK because you've already used notebook at some point. It can get a little frustrating. But here, I'll go ahead and pass this because I haven't used notebook yet, so we'll be fine. So we've made an axis that's 3D. View init, which is, this is sort of like, as I covered in I think the second video, this is like the ideal angle to look at certain things that we have in our data set from. I'm just going to kind of skip over this so I don't explain things forever and ever and ever. GT, all rows. Okay, so our ground truth poses are, they, as I covered in the first video, the ground truth poses are tracked as transformation matrices of the coordinate frame of the camera in each frame in the coordinate frame of the camera when it starts, which is then the global coordinate frame. So for each time step in the sequence, the transformation matrix that is stored in the ground truth at that frame in the sequence is going to be a transformation matrix that relates the coordinate frame of the camera in that time frame to its original coordinate frame. So if I want to plot the points there, then so right here I'm plotting the actual ground truth of the whole circuit that it's going to drive. And so I'm going to take all of the this is a tensor now, so it doesn't really have rows and columns. It has indexes. All of the transformation matrices. And then I want to take the first row and third column of that matrix, which is going to be the x value of the translation vector within that transformation matrix. Now you know that, let me just pull one up to show you. Handler.gt0, as I believe I pulled one up before, but this is what it's gonna look like. So let's not do 0, let's do 10, and look at that. So this 3x3 matrix is a rotation matrix. These three numbers are a translation vector, which tells you the x, y, and z offsets of the origin after the rotation has occurred. And so this will tell you where the origin of the camera in this time step is in the global coordinate frame, which of course is the coordinate frame of the camera when it starts. So if I want this x value, then I need to say first row, fourth column. So that's what I've done here, except that I'm taking all of this number for every one of these matrices. So that's what you're seeing here. Every matrix, I want the x value of the translation vector, and I want all of those. And then for the y, we do handler.gt, all matrices, second row, I think I said third, but I really mean fourth column, handler.gt, all rows, second, it's so hard not to say second, it's the third row and fourth column. And then I want to make that black, because that's going to be like our established ground truth line. And then what I'm going to do is I'm going to trace a chartreuse line over the top of that as we drive the car around. And so we'll be able to see exactly where it is driving at that time. And so another thing that we're going to need is let's watch the disparity as well, because I think that's really interesting and it's fun. So stereo L equals handler dot images left, and this is a generator, and stereo R equals handler dot images right, that's also a generator. So just keeping that in mind, and we need to go ahead and say poses equals GT or GT in handler dot GT. I don't really think that I need to do that, but this is the way I wrote it, so let's run with it. Oh, we're really feeling the generators. Okay, so for each iteration in our loop, we're going to want to generate an image left, so we'll say next stereo L. We want an image right, is next stereo R, and then we're going to want, I'm going to time these things, date time dot now, and okay, so let's make a disparity map, say compute left disparity map, and we're going to take image L and image R, and matcher equals SGB, because it looks way nicer. And so we've generated a left and right image, we've started the timer, we have created a disparity map. I'm not going to do the fancy stuff with the disparity map because I don't know, this is going to be too tough to explain. Maybe I will, but later. So let's get ourselves a P cloud, and that'll be P cloud frames. And you know what I'm going to do? I'm going to multiply this by 255 because I may want to change the color of it. It's not a, if I use CV2 to assign a color map to our point cloud, then we're going to need it to be in a integer 0 to 255 format. Not really something you have to worry about too much if you're just kind of following along for the fun of it at this point, because we won't be using any of this to do visual odometry. Like I said, this is all just for fun. So yeah, the visual odometry is coming in the next video, I promise. And so yeah, let's do disp equals cv2 dot. I'll save this because we can look at the difference later. Okay, so in this case, we don't want this here. We want to call this P-cloud. Okay, so that's going to be the ground truth for this particular iteration that we're on. Okay, so here's where we say x's dot append this ground truth moment of the first row, fourth column of that transformation matrix. Y's dot append the second row, fourth column. Z's dot append GT, third row, fourth column. And then we'll say plt dot plot x's, y's, and z's, and the color, as I promised, will be chartreuse. Because if it ain't chartreuse, it ain't no use, right? It's a fishing joke. For some reason, we need a plt.pause here, so I'm just going to put a ridiculously small amount of time because I don't really want it to pause, but you need a number there. Anyways. So then we're going to do a cv2.imshow, and this one's going to be called camera, and we're going to show the left image, cv2.imshow, and this is going to be the disparity, and we're going to show the disparity. Then the LIDAR is the point cloud, so we've got that, and then the wait key, cool, and then we'll go ahead and set up an end timer. Just kind of space these things out a little bit. Date time, date time.map compute time, compute times dot append and minus start. So this will give us an idea of how long each one of these loops is taking. And then so down here, need to say plt.close also. I think that this should work. So let me switch us over to full screen here. I'm just not confident with my hotkeys. So we are in full screen. We got an error here. I said axim. It's supposed to be asim for azimuth. And yet again, axis on the side. I wrote a 4 because I was talking and I said 4. There we go. All right, we got everything's here now. So we got our LIDAR point cloud happening here. This is our disparity map, which right now doesn't really look great, but we'll tune it up here in a second. And we've got our actual black and white image up here, and we can see our chartreuse line worming its way through the streets of our black ground truth information that we plotted. And of course, we are conveniently already looking at this in a manner which is what is the word I'm looking for? It's it makes sense, you know, z-axis, and it might be nice to actually label these axes. I wonder where I do that. Let's write this over here. Ax dot set x label to x. Ax dot set y label to y. And ax dot set z label to z. Okay, so that's going to fix that. Let's just see if we can get away with closing these. Never. Okay, I dare not tell it to close Python. I wonder if I wrote plt.close a couple of times, if that would do it. Ah, yeah. There we go. Nice and clean. So yeah, so now we've got some axes labels, and that'll make it easier for me to make my point that I was going to make. And so I'm just gonna flip right over here real quick so that I can, okay, so our disparity is not looking all that fun to look at because there's a lot of missing information, but also yeah, I also didn't make it into integer. So it's one of the things to keep in mind with using plt.mshow versus cv2.mshow is that cv2.mshow really does expect integers, whereas plt.mshow will automatically scale max to min. So whatever you give it, it will divide it by the max and take it from 0 to 1 and normalize it. But cv2.mshow doesn't do that. So if we're going to look at things and have it look better, then we want to explicitly make this into disp times 255, and then we'll wrap that up in parentheses so that I can then say has type uint8. And yeah, let's look at the progress that we've made. Cool. All right, run this cell again. Whoa, man, that looks crazy. It's clearly not what I was trying to make it look like, but that is wild, man. I need to get like a screenshot of that and make it into a banner somewhere. It's tripped out. I love it. So yeah, these frames are not lined up because I haven't been using the handler.reset frames. Should probably come. I'm just going to make a separate little cell for that here. We need to line our our images up so that we're looking at the same thing in all of them. So now what happened to that disparity? Because that was something else. Okay, I know what it is, because the disparity is measured in pixels, and I'm multiplying it by 255 here. And so in order for this to work out the way I want it to, I need the disparity to be normalized between 0 and 1. So I need to do exactly what I said that matplotlib does and divide it by disp.max. Although I did love the way it looked. So that was cool. But this will, yeah, okay, so this looks a lot, this looks like where it's supposed to look. Yeah, so we see the brighter stuff is closer to us. Here, down here with the LIDAR, the stuff that is further away is actually brighter because we have our depth set up as such. And this is the actual image up here. So that's pretty neat. And so let's do one last cool thing and use some CV2 color maps. And I'm going to do that right here, and we'll say disp equals cv2.apply color map to disp, and we'll use cv2.color map. And so if you press tab, you'll find some options here, and they're all pretty cool. There is a documentation for this, and so I won't sample all of them. I think that the one that I would like to use is a pretty rainbow. So let's do color map rainbow. And you're not going to be able to see that because I didn't share the full screen. I'll run it again. I'm not exactly a veteran YouTuber / OBS user, so I gotta like make sure that you're actually seeing what I think you're seeing. So there will be a little bit of seeing what I'm recording. Yeah, so I mean, this is looking pretty cool. You can see that, okay, there is a problem though, because the chartreuse line keeps starting in the starting point, whereas these images are not. These are still progressing down the road. And another thing I want to do is I'd like the red to be what's closer to us and have the purple be what's further away. And so what I can do is say, since after we divide disp by its own max, we can then say disp equals 1 minus disp, and then that'll reverse the max and min, because now you'll yeah, it'll just switch it around, because when you divide something by its max, it normalizes so that the minimum becomes, you know, closer to 0 and the maximum becomes 1. So then if we subtract that from 1, then the max will be closest to 0, and whatever was close to 0 will then be 1, should be the max. And all it's going to do is just switch the colors around because I think it's prettier. And the reason that the poses are resetting every time is because I have set up this handler, or I mean the generator there instead of here. So your generator should be reset together. And then now we should have it, yeah. All right, so we have red is the closest to us. Obviously, there's some noise in here. We have a LIDAR image down here that's doing its thing. You might notice that this looks kind of funny, and that's because I think that these are being scaled. But anyways, I mean, it's all here. It's just looking pretty cool, and I think that this has been a fun video, and so let's go ahead and call it there. And I hope you enjoyed this little exploration into our LIDAR point clouds, comparing the depth between our LIDAR and our stereo estimation, and then also playing around with doing some video generation with CV2. So see you in the next video when we actually do some feature matching and visual odometry. See you then.